Hi everyone, and welcome to this lecture on composite. The importance of this lecture is that composite is really used by every field of dentistry, whether it's general dentistry, pediatrics, endodontics, ortho. So it's an important lecture that will stay with you for life, really. So first of all, very briefly, just a little history before we get started. Restorative dentistry, as you probably know, seems to be or have been around since about 3000 BC in Egypt, and nothing really changed a whole lot until about the 1800s when amalgam started to be placed, and the first aesthetic restorations was methyl methacrylate, and I'll let you think for a moment about where you might have run across methyl methacrylate. But methyl methacrylate was used in the 1930s as a restorative material. So basically that's what we use now for plastic dentures, acrylic dentures. And it's funny to think that at one point we used that as a restorative material. I don't believe you've started working with methyl methacrylate, but when you use these acrylics you'll see that there's a very large amount of shrinkage. And that is, as it sets, it shrinks quite a lot, so it's quite difficult when you think about it to fit it to a specific space, because as you work with it, it's shrinking actually, so that makes it quite challenging. Next thing is it's not really wear resistant, so that's another challenge for a restorative material. Then later on in the 40s we started to add quartz particles. The thing about quartz is it's already set, it's already at its final size, and so as it was mixed into the methyl methacrylate, it reduced shrinkage, and this made it a little bit stronger, and it reduced the shrinkage as well. And then in the 50s we started to develop the first real sort of composite restorative materials. Harvard requires me to make these disclosures. As you can see, there's a few interactions with dental companies. I want to assure you that the presentation today is going to be based on evidence and not my opinion. So there it is. So this is an important summary, I guess. We'll go into some detail, but this is an important summary that there are these 6 important items, I guess, that make up the composition of a composite. Organic BIS-GMA, inorganic filler, silane coupling agent, photoinitiators, pigment and UV stabilizers. So we'll go into a little bit of detail on each of these. Bisphenoglycidyl methacrylate, that's BIS-GMA, and this is the molecule. This is how it looks. Now, BIS-GMA is the polymer form of methyl methacrylic acid, and you can start to see there we haven't changed things tremendously since we started with composites, still sort of using methyl methacrylic acid as part of it, but now indeed there's a lot more complex molecules involved. Okay, the next thing, so I should mention BIS-GMA forms the matrix. It forms, I guess, the skeleton of the restorative material. The next thing is the filler particles. So filler, as you know, back in the 40s they used quartz. Now we still use quartz sometimes, but we mainly use silica. And the filler particle, just like back in the 40s, is intended to add strength. Next thing is the silane coupling agent. Now, silane coupling agent is basically 2 reactive chemical groups bonded to a silicon atom, and this bonding facilitates a connection between filler and BIS-GMA, which would not otherwise happen. So in making a composite, the inorganic filler actually has to be treated with silane coupling agent to facilitate this bonding. Okay, photoinitiators. Clearly they initiate the polymerization process, and a modern example is camphorquinone. So I think what's interesting and important is that this gets activated within the range of normal visible light. You can see here around about 468 nanometers. Photons associated with this frequency range are absorbed by the camphor quinone, and it raises it from the ground state to an excited state. And that is what initiates the process of polymerization. Next thing is the pigment. Quite important, of course, because aesthetics is an important part of composite resins and an important advantage over its predecessors, older composites as well as amalgams. So with pigments, we can add color and control the shade, and we usually now use metal oxides to facilitate that. UV stabilizers resist the discoloration on sun exposure, and this is an example, the molecule down below, but you don't really need to know that, just for interest's sake. So is it that simple? Is it just those 6 little things? Well, really it is. There's a couple of more little details that we'll talk about, but it's really those 6 important things that make up a composite resin. Okay, so firstly, the matrix is not just bis-GMA. So there's a little bit more to it than that. There are diluents and cross-linked diluents. They reduce the viscosity of the material and make it easier to work with the material. Next thing, there is actually a little bit to know about fillers, so we'll spend a little bit of time chatting about that. Fillers can be extremely variable, from 1 to 100 microns in diameter. And as we mentioned, quartz and silica are sort of the most common examples still now. Now, filler particles vary for each composite, and that actually contributes a lot to the material's properties. So this is a rather important slide to think about. It talks about, at the top half, all the different types of composites that there are, from mega fills to nano fills. Nano, of course, the smallest filler particles. And here are some examples of some common composites. If you look on the right column, you have the brand Adaptic and Concise, and these are composites that have quartz or glass filler, and they're about 20 microns in diameter. Adaptic and Concise are very common composites in the market. Durafill is another common one. Silux and Silar, perhaps not as common, but still around. And they are microfill composites, 0.04 microns, and the filler is fumed silica. And I'll let you think for a moment about where you might have run into fumed silica. Next thing here is Herculite and Charisma and Z100, Z250. So actually, Herculite and Charisma we have in the teaching practice, and you can use them basically. So they have quartz or glass filler, and they are small hybrids because the particles vary in size actually from 0.5 to 1 micron. Next one here is Bis-Fill and Clear-Fill and P50. We don't really have that in the teaching practice, but they are mid-size hybrids. They vary from 1 micron to 3, and they have quartz or glass filler. So fumed silica. Where might you have run into fumed silica? Basically, it is a thickening agent that is used in industry. In fact, I reckon it's added to milkshake to make them thicker too. And the place where you might run into it is it's actually in cosmetics, because fumed silica kind of diffuses the light when the light is shone against it, and it gives kind of a softer look. So that's where you run into fumed silica. Okay. So just the matrix and the filler. The matrix is a very reactive thing, you know, the skeleton that we talked about, and bonding is quite weak. The filler is inert, and actually the more filler you have, it improves the physical properties of the material. Okay, so we'll spend a bit of time talking about classification of composites, because there's actually three different ways that we can classify them. First, by initiation techniques, filler size, and then by viscosity. So let's chat briefly about that. By initiation technique, they can be light cured, chemical cured, or dual cure. So chemical cure, of course, means they set by themselves, and light cure means they are initiated by light through the photoinitiators. They can be classified by filler size. So as we've talked a little bit, you can have microfills, macrofills, hybrids, megafills. So there's a variety of classifications there. And then the third thing is by viscosity, because we can talk about flowable composite, and I'll let you think a little bit about what properties might be different here between these three. So flowable composite, regular composite, and the more recent packable or condensable composite. So I wonder what might be different here between these three things. Actually, really it's the filler. So the flowable has very little filler. Regular has a bit more filler. Packable has lots of filler. So packable, still working on that, I reckon, because even the newest packables are not so terrific to work with. They're a little bit tricky. It's not like packing amalgam. It's not quite so nice and clean and convenient, but there is a lot of research going on that, and hopefully that will there will be a solution to that soon. The beauty of a packable composite is in the same way that you pack amalgam, you can pack it. Say you're doing an MO, you can pack the amalgam and get a really hard, tight contact. With composite, that's a bit harder to achieve unless you pack it. So that's why it's important to develop a good packable composite, because then we can do really fantastic contacts. At this moment, you can do good contacts. It's quite challenging, quite technique sensitive. Okay, let's move on. Okay, the advantages. Of course, aesthetics is the big advantage. There's many shades available. You can combine shades. We also have opacers available. So if you have a stain or you have a post or something like that, you can place the opaker, which will inhibit that dark shade going through, and then place the composite on top, and you can get quite an aesthetic result. Another advantage is conservation of tooth structure. Basically, if you think back to amalgam prep, you have to first clean the caries, and then you have to prepare the cavity to receive the filling. So you have to create retention, mechanical retention. You don't have to do that in composite as much. So you can have round line angles, and the preps can be smaller. And caries dictates the shape of the prep and not your need for mechanical retention. So you can be more conservative. Next thing is protection of tooth structure. I've put a question mark there. So let's try and explain this. So basically, amalgam does not bond to tooth, right? Composite does bond to tooth. Okay. So what happens here is, if you have a sort of quite a broken down tooth, you can put in a composite, and then those. Say you've got a thin shell of a tooth, like you've got a big MOD restoration. If you had an amalgam, that buccal and lingual enamel is not very secure, you know, and in fact, there's a high likelihood it might fracture, because every time you bite on it, that enamel wall has to function on its own. With composite, in the same situation, the composite would bond to those two buccal and lingual enamel walls. Therefore, when you bite on the wall, some of the force is transferred through the bonds into the composite and even to the other side, so it distributes the force a bit better. And so the force on that one wall theoretically is less. And the question mark is there because, you know, if you do a big composite, that's actually not as ideal as amalgam, strength-wise. So it's sort of a give or take, but that's one thing that composite can help with in certain situations, and you really have to think through which is the right case to do that, because a composite can distribute the forces theoretically to the whole tooth through its bonds, thereby reducing the point force at the point of impact. couple more advantages. It's non-metallic, and this means a couple of things. There's low thermal conductivity, and there's no galvanic currents. So we can talk about galvanic currents when we meet in person. The other thing about non-metallic is it's aesthetic as well. Disadvantages. There are several. The first one is wear. Composite is less wear resistant than amalgam. Next thing is it's very technique sensitive. We'll talk briefly about the technique, but you know, a highly trained monkey could probably place an amalgam, but it's very tough to place a good composite. It's very tough to get a nice contact. So that's a great challenge. Saliva protection from saliva is very important. This increases the chairside time, of course, and that increases the cost. And the last thing is that the coefficient of thermal expansion is larger for composite than tooth structure. So thermal expansion is that property of a material that changes the volume at different temperatures, and composite is worse than tooth structure. So the problem with this expansion reduction for temperature is it can lead to failure and microleakage. And then, of course, secondary caries due to shrinkage. So composite shrinks when it sets. And I apologize for this slide, but if someone has a better idea to convey this information, do tell me. But basically, what I'm saying here is you start off with small particles, you finish off with a polymer when it's light cured, and there's a lot of dead space between the small particles which goes when they bond together. Therefore, there's shrinkage of the material. The material literally becomes smaller when you set it with light. So the problem here is you place your composite, shape the contacts very nicely, shape the margins very nicely, and then you cure it and it actually shrinks. And so the margins are not how you wanted, the contacts are not how you wanted, and so it's very challenging, and we'll talk about a couple of techniques to manage that. Okay, another disadvantage, this is the polymerization shrinkage that I was talking about. It can lead to open margins, like I said, cuspal fracture, and the reason with that is if the composite is bonded to a cusp and then you cure it, through the bonds it could pull those cusp parts together and put tension on the cusp, which could lead to the fracture. It could lead to craze lines, and it can lead to post-op sensitivity as well. Okay, now this is a 2011 study looking at a new generation of low shrink composites. 4 such composites were tested, and 2 were found to significantly reduce the shrinkage but not eliminate it. So seems very difficult, so it seems impossible to eliminate polymerization shrinkage, so we need to be able to know how to work with it. Here's another study. This study is looking at the ratio of bis-GMA and TEG-DMA and how that impacts polymerization shrinkage. When that happens, when polymerization shrinkage happens, you have an internal stress created. And this study, for the first time actually, showed that the resin matrix showed a stronger influence on polymerization shrinkage, polymerization stress, and the filler showed stronger influence on shrinkage. So there's no way to prevent polymerization shrinkage. We can only minimize its effects. This is another study here, polymerization shrinkage and polymerization shrinkage stress in polymer-based restoratives. You can see this conclusion here, as no method for handling the adhesive restorative materials has yet been described which guarantees a leak-proof restoration, a practitioner has to accept the problem of polymerization shrinkage and destructive shrinkage stress. Only a proper understanding of the mechanisms that cause these problems and the techniques that may reduce their effects will enable the practitioner to do good dentistry, basically. Okay, minimizing these disadvantages. So these are 3 facts that I want you to know up front, and then we'll talk about how we can use them. Okay, number 1, shrinkage we know happens towards the light cure unit. So when you place a light on a composite, it shrinks towards the light. Next thing, marginal adaptation is better with slower rates of polymerization. So if you can slow down the process a little bit, you actually get better marginal adaptation. And then restoring in increments reduces polymerization shrinkage. The reason there is if you put in a big hunk of composite and cure it, you get a big shrinkage. If you put a small layer, you get a small amount of shrinkage. Then you can place your next layer, which can compensate for that shrinkage, and then the second layer shrinks a little bit. Then you put the third layer, and so on and so forth, and you can end up with much less shrinkage. Okay, so I want to work through this basic case. If we are restoring this corner of an anterior resin, this is the direction we want it to cure towards the tooth. Okay, so this is the direction in which you would place the light cure, which is, it seems strange, because it's probably not how you think in your mind, but we actually want to do it this way so that it cures towards the tooth. And then of course we would finish off and cure the rest. Now, one comment is, this is an anterior tooth. Now sometimes it's not always possible to do this fancy stuff like this, you know, to make it cure in the direction. So you've got to sort of use your knowledge and your sort of clinical skills and put it all together and try and get the best result. But say you're doing a wisdom tooth, it's not as easy to make it cure towards the tooth as it is here with this front one. This is the wrong way to do it. This is, you see, allowing it to cure away from the tooth, which creates sort of a gap there and mucks up the margins as well. So this would be the right way. First of all, put the light here, the shrinkage happens towards the light, then up here, shrinkage happens towards the light, and then finish off by curing the top as well. So this is one problem with that we just briefly described of curing without making increments. So if you have one big hunk of composite and try and cure it here, you may get this gap as the whole material shrinks towards the light, and then that can lead to fracture and fracture lines and all sorts of difficulties there. Okay, so there's a lot of information here and you can pause it and check things out, but basically the highlights here are composite is an unforgiving material. It's very technique sensitive and it's much more challenging to work with than with amalgam. Once you've got some experience, you know, amalgam can seem difficult at first, I guess, but once you've got some experience, it's basically packing in an amalgam. Composite, there's so many other things to manage and deal with. Next thing is composite is more expensive, and of course, I don't need to tell you, much more aesthetic. The next important thing is that you can produce a more conservative prep with composite, because we're not led by creation of retention. We're really led by caries when we're preparing the tooth. Folks, I'd like to switch gears a little bit and talk about the evolution of dental adhesives and dental bonding. Okay, folks, if you look at this slide, you can see some of the things we've already talked about today. First of all, you'll see the progression from self-cured to visible light cured. And see, there was a period where we used UV light, and patients still sometimes talk about this because it wasn't that long ago actually. Next thing is you can see the development from macrofill to midifills, microfills, and then now nano hybrid composites. And we can talk a little bit about the differences in properties of these when we meet in person. I'm going to talk today about the bonding process, acid etching, and that kind of thing. GV Black. So hopefully you know GV Black. GV Black, most famous for developing the cavity classifications, considered the father of modern dentistry, I guess. He was dean at Northwestern University School of Dentistry. Unfortunately, that school closed in the 90s, but it was a great school in Chicago. One criticism, I guess, is that G.V. Black believed in extension for prevention, because he believed restorations cured caries. And of course we know better now, but he believed that grooves and risk areas needed to be drilled out and filled because that would prevent caries. But of course, he didn't know about secondary caries. Okay, Michael Buoncore in 1967 described a process for enhancing the adhesion of plastic to teeth, and that's how modern composites and modern dentistry began. Michael Buoncore was from Rochester School of Dentistry, and he is accredited with being the first to use modern composites. He developed etching techniques for dentistry, which is still used today. What's remarkable, I think, is, well, this is a paper he wrote in the 1940s, and in order to, what he said is, we need, number one, to alter the tooth surface to facilitate bonding, which we do with etching. We'll talk about that. Number two, to use coatings, we needed to use coatings as an adhesive interface between filling and tooth, and we do that too. So it was amazingly insightful back in the 40s to think like that. So a quick refresher, I guess, of dentin and enamel. You can see that enamel, primarily hydroxyapatite, 96% mineralized, highly mineralized, most mineralized substance in the human body. The composition of dentin, quite different. They have tubules and it's permeable. It's 20% organic, much less mineralized, and therefore less brittle. And the other thing, I guess, is it's somewhat alive because it continues to form throughout life, and that's not the case with enamel. You can see here the interrod and the rod enamel. Okay, enamel bonding. So how do we bond to enamel? Basically, we use an etching process. Like I said, Michael Buoncore described that all those years ago. What etching is it produces, the etching process produces a pattern or design on hard material by eating into the material surface. You know, in industry we talk about etching metals, but in dentistry we etch enamel, and it does the same thing there. It kind of eats into the surface and creates what we call microporosities. We use 30% to 40% phosphoric acid for 15 seconds. It's a strong acid, and there's basically three types of patterns that can develop. Type 1 is a pattern where predominantly the rods are dissolved. Type 2 is a pattern where predominantly the area around the the area around the enamel rods are dissolved. And type 3 is a pattern where there's no evidence left of the rods. So basically, you don't need to know all that, but you need to know that it selectively dissolves enamel rods. And like I mentioned, creates microporosities. Here is an image of those microporosities. Now, by creating microporosities, you can see that instead of having a flat surface, you have these porosities, and therefore you actually have a greater surface area to bond your composite into. The resin can flow into the microporosities. When the resin does that, we call that resin tags. Is enamel bonding that simple? Well, actually it is that simple. The only real trick to it is that restorative resin is too thick to flow into the microporosity. So we use unfilled resin, or which we sometimes call adhesive resin because it's doing the adhesiveness. So less filler means more flowable. Okay, and the other trick to know is that we need to bevel the enamel for best results. Now, what is beveling? Beveling is basically having a gradual end to a restoration rather than an abrupt one, and what it does is it increases the surface area for bonding. And you may be familiar with beveling from woodworking or other stuff like that, but we can talk about that when we meet in person as well. Basically, bevel increases the surface area for bonding. Why bevel? Well, number one, it increases surface area. But also it can lead to more aesthetic restorations, and we can talk about that when we meet in person. Why not bevel? Well, you have to be cautious because beveling can produce thin portions of enamel which are more likely to fracture. So you have to think about it, how you prepare your tooth and where you bevel and that sort of thing. Okay. So these little guys, very cute little guys, are odontoblasts. These are living cells in the dentin. So clearly it's very different environment to bond to dentin than when we bond to enamel. We have to be much more careful. Okay, so in dentin we also have to deal with the smear layer. What is the smear layer? It is adherent debris that's produced when cutting the enamel or dentin during cavity prep. This is the smear layer right here. So we're going to talk about that. Here it is. So this is the smear layer. Okay, and you can see it's kind of plugged up the tubule here. Okay, so this is sort of a diagram of the same situation. You can see the peritubular dentin, the smear plug, and the smear layer. And you can see that the smear layer has these water-filled channels. And actually, we can use this actually for bonding. The good thing about this plug is it's going to reduce sensitivity, because if the tubules were open, you can actually be the tooth can actually be sensitive, but this plugs that, and we can also use this smear layer for bonding. Okay, this is what we need for dentin bonding: a conditioner, a primer, and an adhesive resin. We know what an adhesive resin is. We'll talk a bit about primer, and now the conditioner is essentially a weaker acid. It's a 10% polyacrylic acid, and it sort of cleans the tooth surface to improve adhesion. Can also use 20%. And the primer, what is the primer? It is a bifunctional monomer with two active bonding positions, so it facilitates a bond between dentin and the unfilled resin. And then adhesive resin, like we talked, it's unfilled or very lightly filled, and therefore it flows more easily into the microporosities. Is dentin bonding that simple? Unfortunately not. It's a little bit complex, so let's chat about that. Basically, there's two different strategies: the etch and rinse strategy and the self-etch strategy. Okay, so let's talk about that. The etch and rinse strategy is there is a separate etch, a separate primer, and a separate adhesive resin. That's what we've talked about so far. The self-etch strategy actually combines the etch and the primer together, and then you would have a separate adhesive resin. So it's fewer steps basically. Okay, so what I want to show you in this slide is the hybrid layer. This is a layer that contains the smear layer impregnated by resin, by unfilled resin. The smear layer is not gross debris, it's very fine, and you can't really see it with the naked eye, but here is the smear layer. We've seen a similar slide to this already. And this is the resin impregnated layer. And on top of that, you can have adhesive and then your composite. Okay, so we can talk a little bit more about that. So this is the same thing, okay? Same thing here. You see the hybrid layer, the adhesive, the composite, hybrid layer, adhesive, composite. And now in a sort of enlarged. Okay, so these are the two strategies. You see there's the etch and rinse strategy, the self-etch strategy. Now the etch and rinse, separate etch, separate primer, separate adhesive, but it's not so simple as that, because dental companies have also created this acid etch and primer adhesive combo. So fewer steps. And then over here on the self-etch you have an acidic primer. Therefore you don't actually etch, so you have an acidic primer that's not washed away. It's just dried, and then the adhesive, and then composite. And then here all in one. So this is the quickest and easiest. So why would you muck around with this when you've got this? Which is better? So let's talk about that. Now, here is a study. This study compared the 3-step etch and rinse to the 2-step etch and rinse to the 2-step self-etch and the 1-step self-etch. What they found was that nothing is perfect, which is a shame. And enamel bonding was more effective with the 3-step phosphoric acid etching, and OptiBond was one of those adhesives used. And I want to mention that because we use OptiBond in the teaching practice. So you'll meet OptiBond if you have not already. Now, this is another study comparing etch and rinse strategies to self-etch strategies. And it found that the etch and rinse is superior to self-etch. They had better marginal seal, better marginal adaptation, but interestingly in 2 years neither of these restorations failed. The 3-step or the self-etch, they didn't actually fail, but the seal was better. So I guess the point there is you might see stuff that doesn't look perfect, but you really got to think, do we really have to replace that or not? So because composites age quickly, they're not as wear resistant, you've just got to think a little bit about, when is it appropriate to replace a composite or just leave it and watch it for 6 months. Here the same results from a different study, that the etch and rinse system is more effective but still not perfect when compared to self-etch, or indeed the all-in-one technique. Okay, so the dentin must remain slightly wet. You should dry it but not desiccate it. Drying it too much will cause the collagen to collapse, and when the collagen collapses, the bonding is not going to be as good. Quick refresher: how do amalgams stick? What causes retention? Well, basically it's all these things. It's a mechanical bonding process, isn't it? There's grooves, slots, pins, posts, and undercuts. Okay. Now, what makes composite stick? Is it chemical? Is it mechanical? Actually, it is micromechanical, because remember, there are resin tags formed, and it's not actually chemical. It's still mechanical. It's just at a very microscopic level, I guess.